Freeman Dyson is a theoretical physicist. As he said, the first 50 years of his life, he did outstanding theoretical physics. He came to this country after World War II, went to Cornell, worked with two of the great physicists, Richard Feynman and Hans Bethe. He did seminal work in unifying or giving a unified picture of quantum field theory at that time, and Cornell University, to its credit, made him a full professor when he didn't even have a PhD. Whether they knew he didn't have a PhD or not, I don't know. But he didn't have a PhD and still doesn't have a PhD. Although I think we could give him a PhD just after his talk here today, just by the power vested in me by nobody. He's written a number of books, and in fact, he's about to be outstripped by some of his children who also write books, and he will talk about the books. But you have, all of you, I noticed, the brochure which tells you the books, and I suppose as soon as the day is over, you can go off to the Eagle stores and buy his books. Does Eagle sell books? No. Oh, well, someday. Anyway, without further ado, I want to introduce Dr. Freeman Dyson.
Good. Anyway, thanks for coming, and thanks for the lady who invited me here. And so let's have some questions. I didn't come to give a speech. I came to talk with you, and so let's hear from you. Don't be shy. Thank you.
Do you think it might be possible to travel?
Microphone, because we're taping this. Would you be kind enough to write down?
Oh,
Thank you.
do you think faster than light travel might be possible someday? And if so, do you have any ideas how?
Well, I hope it's not. I mean, to me, it would be a disaster if we could travel faster than light. I just, because I value my privacy. And the wonderful thing about the universe as we know it is that you have this speed limit of nothing can travel faster than light as far as we know. And that means if you get far enough away, you really are on your own. And the taxman can't get at you, and your mother-in-law can't get at you. I think that's precious. It would really be sad if, no matter how far away you go, that people could still talk to you and that you'd still be entangled with all the unpleasantnesses that you wanted to escape from. So anyway, that's my view. Don't have to agree with me. The whole point is, of course, not to agree, but just to hear the other side. And so I would say, if there is a way of traveling faster than light, it would be a disaster, and I can't think of one that makes sense. But of course, I'm prejudiced.
Thank you.
What would you categorize as your greatest accomplishment so far?
So what's my accomplishment? I don't know. I would say raising 6 kids, and all of whom are more or less, all of them self-supporting and sane. But no, I mean, I always said that in my life there were sort of 3 priorities: family first, friends second, work third. And I think that's still true. That so whatever I've done in the way of science is by the way, compared with what I've done in raising a family. You don't have to share that, of course, either, but that's the way it is for me. So science has been tremendous fun, but nothing I've done has really been very important. And it's, I suppose, you never can tell, of course, what might be important after you're gone. I would say that the most important thing I probably have done is writing books. The books I've written have been mostly addressed to sort of public questions concerning the future of mankind and the political and legal and human problems. So those books might have had some influence, certainly much more than the influence I've had just doing physics. Yes.
What do you think is the question in science that it will be the most important, like a recent discovery that would be coming rather soon? What would you think would be the most important one?
Yeah, well, I don't know what you mean by recent. How far back do you want to go?
No, I'm not talking about in the past. I'm talking about what would you think would be the most important future discovery?
Oh, future discovery.
Yes.
Well, of course, by definition, the most important one is the one we haven't a clue about. It's anything that we can predict, of course, is almost automatically not so important. But, I mean, if you think of the things that we can predict at the moment, I suppose the figuring out how the brain works is really the most important. So it's almost sure that'll happen. I would guess that in the next century, so neurology will be more important than the rest of science. I mean, today probably genetics is more important, but after another 50 years, genetics will be starting to be less exciting, and neurology will then be moving forward. But it's hard to tell, of course. But I would guess that. And so, if you want me to guess, I'd say figuring out in detail how the brain functions and all that goes with it, human feelings, human emotions, and human behavior as well as knowledge. Once those things are really understood, it'll have profound effects, of course, on everything we do. Yes.
Do you think that scientists will ever be able to come up with like a unified theory of all science put together?
So do I think there'll be a unified theory of all science? I would say I hope not. I think that it's much more interesting to have a big diversity of ideas, big diversity of subjects and disciplines. And as far as I can see, that's going to be the way it'll be. But of course, I could be wrong. I'm frequently wrong. But as far as I see at the moment, of course, there is a big argument going on perennially between the sort of unifiers in science and diversifiers. And the person who is most strongly advocating unification at the moment, I suppose, is Ed Wilson. He wrote a book called Consilience, which some of you might have read. And I think it's an interesting book, even though I disagree strongly with it. And it's quite readable and quite short, so you might like to read it. So Ed Wilson's putting the view that essentially all science will be unified by this process he calls consilience, so that ethics will be reduced to psychology, and psychology will be reduced to biology, and biology will be reduced to chemistry, chemistry will be reduced to physics. And I mean, so of course, always physics ends up on top, which is something I don't approve of. And anyhow, I profoundly disagree. I would say that the tendency in the last 50 years has been the opposite. That on the whole, the biological sciences have been racing ahead using tools from physics, but not using ideas from physics, so that the biological sciences have tended to become more and more independent. And I hope that will continue. Yes, somebody at the back, good.
I just wanted to know what kind of background you had as far as education and previous jobs before you got into physics.
Yeah, well, I grew up as a privileged kid in England. So my father was a school teacher, which in those days meant something. He was... He had an absurdly small teaching load by present-day standards, and lived a very interesting life, and frequently went traveling. So I was put away in a boarding school. Which was among middle-class families in England, that was the custom, that you sent the kids off to boarding school so you could enjoy life. And anyhow, I was at a boarding school, a little bit like this one, except that it was 600 years old instead of 20 years old. But it was an elite school, and I was terribly hostile to the school. I was a real young rebel. I thought the school was terrible. But looking back after 50 years, I've mellowed, and now, of course, I think of it now as being not altogether so bad. And it certainly did give me a good chance in life. It was a school that concentrated the bright kids in one place. So I had a lot of friends who were very bright. I learned much more from the kids than I did from the teachers. Probably you do too. And so I was lucky. And then the best of all was that World War II began when I was 15 years old. So I was just halfway through high school. And at that point, England then became essentially isolated from the rest of the world. And we were blockaded by the German submarines, and so we only could import the absolute necessities of life. So we imported food and we imported guns, but we couldn't import paper. And so the result of that was there was no paper, and the result of that was there was no exams. Was in England, the oral exams had not been invented. So all the exams we had were written, and since there wasn't any paper, you couldn't have exams. So that was a wonderful time to get an education. So on the whole, I was lucky, and and a lot of the teachers were away at the war. And actually, my last year in high school, I was 7 hours a week I was in class, actually. And that was, so it was a good life. We were very free. Most of the time we could do what we liked. And after that, then I went to college briefly, and then I went to work for the war. But I think the years I spent at this high school were certainly quite decisive, and that's where I fell in love with mathematics and became a mathematician. And then, so I was trained as a mathematician, and then only after that went into physics. And for me, I mean, physics is really applied mathematics. But what I do is always mathematics, although it's called physics. Yes.
What do you think is the most exciting new idea or change in the way that scientists think that you've seen in your lifetime?
So, well, I don't know. I mean, one of the things that really I found most exciting, I mean, as an idea, was Stephen Hawking's discovery of Hawking radiation, which is, I mean, this is all rather technical. This is something I'm talking now as a scientist, Stephen Hawking got this idea that black holes are actually not black, that they radiate all the time, thermal radiation, so heat radiation at a very low temperature, and so that black holes, in fact, don't live forever. They gradually radiate away their mass, and finally then explode in a burst of fireworks. And so every black hole in the long run will just disappear in a burst of radiation. That to me is a profoundly original idea, and I think the most unexpected thing I've seen happen in physics during my lifetime. But I can't claim that it's important for anybody except physicists. Yes. If you talk about science beyond physics, then the double helix certainly was the most exciting thing.
What can you tell us about like the fourth and fifth dimensions?
Well, the fourth dimension is time, and that we're familiar with. And the interesting thing about it is that Einstein discovered it's mixed up with space, so that there's no absolute separation between space and time. Depends on how you're moving. So that, and if you fall into a black hole, then your time becomes turned around, so it becomes space, and your space gets turned around, so it becomes time. So that the two things are essentially the same if you look at them from a mathematical point of view. The distinction between space and time is only a local distinction. So that's all very exciting as a intellectual game. The fifth dimension, of course, is completely speculative. We don't know whether there is any fifth dimension. There are various five-dimensional theories which now are quite fashionable, and they are even being experimentally tested by doing experiments on gravitation at very short distances, finding out whether the Newton's law of gravitation holds below a millimeter in distance. And if it doesn't, then maybe you have evidence for a fifth dimension. But that's very speculative, and there are even more speculative theories that there really are 11 or 12 dimensions. Maybe it's right, maybe it's not, we don't know. But anything beyond 4 is certainly completely theoretical without any evidence to support it. Yes?
Do you believe the universe possesses enough mass to collapse in on itself? In other words, is it hyperbolic in nature or Euclidean?
So it's the question whether the universe has enough mass to collapse under its own gravitation. And the answer is undoubtedly no. We know that the amount of mass in the universe now, this is only within the last 10 years, we know that the amount of mass is definitely not sufficient to cause it to collapse. The interesting question today is whether it is just expanding linearly with galaxies going away at constant speed, or whether it is accelerating so the galaxies are actually moving faster and faster as time goes on. That's now the hot question, and there's a lot of evidence just in the last 2 years that we're actually living in an accelerating universe. So it's expanding even more rapidly than we had thought. That depends, of course, on observations which are going on today, which really only tell us what the universe has already done. It doesn't really tell us what it's going to do. And there are two versions of the acceleration, one of which is called the cosmological constant, and the other is called quintessence. And those are both sort of competing theories of the expansion. And if the acceleration is caused by a cosmological constant, which was Einstein's idea, then it continues forever, and that's a very bad situation for humans if we live that long. It means that the universe becomes very boring after a short time, that the galaxies are accelerating so fast, they continue accelerating, that they all disappear over the horizon in quite a short time. So you're left with a profoundly boring universe in which there's absolutely nothing outside our galaxy and a couple of neighboring galaxies. Beyond that is just nothing but blank, empty, blank space. And so I hope very much that's not the way it is. It would be a really dismal prospect to look forward to. The hope is, if you believe in the acceleration, that it might slow down, and that's called quintessence, the theory that the acceleration is caused by some kind of extra field, which is known as quintessence, meaning sort of as the fifth field. And quintessence predicts that the acceleration will slow down. So although it's accelerating today, in the end it'll slow down and just expand linearly. So you'll be left then with a linearly expanding universe, in which case the other galaxies continue to move away, but at least they're still visible. So you can talk to your neighbors even if you can't travel. Yes.
I was wondering, what are your opinions on time travel? Do you think it would be possible to ever go back in time? And if so, how? And if this happens, what do you think would be the effects on, like, maybe society and physics and everything?
Yeah, that's a delightful subject. I have a friend called Richard Gott in Princeton who actually invented a time machine, and it works. I mean, this is not kidding. This actually works, and all you have to do is find two cosmic strings that are moving relative to each other. Well, what is a cosmic string? A cosmic string is a line which goes through the universe, which is a singularity in the space-time, so that you have, as you go around this line, it's less than 180 degrees, less than 360 degrees as you go around. So it's a sort of a conical singularity as you go around it. So if you can find two of these cosmic strings and get them moving one relative to another, then you can build your time machine. And the time machine then actually works. You have a rocket ship, and you can describe a curve that it goes along, and you have to just to zoom around these cosmic strings as they're moving. And the effect of it is you go around in a spiral, and you come back and you find it's earlier than it was when you started. And so that's actually mathematically correct. So it only leaves you with one little problem, that's to find your cosmic strings. The effects of this, of course, if it actually were built, the effects on our lives, of course, would be quite interesting. But that I leave to you to speculate about. You can go back and shake hands with your grandfather, and of course, the problem there is that if you might persuade your grandfather to marry somebody else, and then you wouldn't be the grandson. And so you get into some difficulties there with causality. But anyway, that's a problem that has to be dealt with after you've found your cosmic strings. Yes?
Could you explain to us the concept of the Dyson Sphere and how you went about coming up with the idea?
Yeah, well, I talked about that before, but I guess you can have it. This is a different bunch of kids, so I'll talk again. Anyway, that was an idea which came out of the search for extraterrestrial intelligence, that is, for intelligent aliens somewhere in the sky. This was suggested that we should search, I think in the year 1959, by Cocconi and Morrison, who were two physicists who lived at Cornell, where I was at the time. And so they suggested that the aliens might be communicating with each other by radio. If you do the calculation, you can calculate that with our existing radio telescopes as they existed in the 1950s and the existing radar transmitters, that you actually could communicate over something like 100 or 1,000 light years, because radio communication is just so extremely sensitive. So if you had one version of the Arecibo telescope here and another Arecibo telescope 100 light years away, they could exchange messages with each other. So you could imagine the aliens might be trying to communicate with us. They might be sending radio signals, and in that case it would be interesting to listen. So Cocconi and Morrison then suggested we should listen for these radio signals, and Frank Drake, who was a local radio astronomer, actually started listening at the Green Bank telescope, and the listening for radio signals. The program, which is called SETI, standing for Search for Extraterrestrial Intelligence, has been flourishing ever since. We have still a flourishing enterprise of people listening for radio signals, but nobody's yet heard one. And anyhow, I thought when I heard about this, and it's all very well to listen for radio signals, but there might be a lot of aliens out there who are not communicating. For some reason or other, they're not interested in communicating. So how about that? What should we do to detect non-communicating aliens? So I thought, well, isn't there something else you could listen for? And the answer is yes, you could. If an alien civilization has a population that's out of control like ours, that it will be multiplying exponentially, it will be using more and more energy in order to live. So in the course of time, it's only a few thousand years, if you're growing by 1% per year or something like that, that they will use all the energy of a star in order just to live and feed themselves. And in that case, they'll have a severe problem with waste heat. According to the second law of thermodynamics, if they're using that much energy, they have to radiate away the energy into space to get rid of it. And so it'll be seen in the form of infrared. So I wrote a little paper in Science magazine, one page it was, entitled Search for Artificial Sources of Infrared Radiation, suggesting we should look for infrared in the sky, not only for radio signals. And at that time it happened that the Air Force was flying satellites looking at the Earth at night in order to watch for missile launching, and so these were quite sensitive satellites. So they were taking pictures of how the Earth looks at night from 3,000 miles up or so. And everything you could see on those pictures was actually man-made. The infrared is in fact the best channel for looking for human activities. So if you wanted to see what humans are doing on the Earth, you should look for the infrared. And so you could see all kinds of interesting things going on. Well, I unfortunately made the mistake of using the phrase artificial biosphere to describe what we were looking for. I was thinking that these advanced civilizations, which are using all the energy from a star, they have to have a big surface in order to radiate away the heat. And that's the outer surface of the habitat where they're living. So you have the aliens living on this habitat, which could be any shape you want, and probably just a lot of orbiting balloons going around the star or something like that. So the outer surface is what you're looking at. And I called this an artificial biosphere, just meaning a habitat. But unfortunately, the science fiction writers then misunderstood that to mean a solid sphere, a big round ball. And that's what you saw on Star Trek. But that's not really the way it would be. And because a big round ball like that, of course, is mechanically impossible. Yes? Needless to say, nobody's yet seen one of these artificial infrared sources. The problem is that we now have infrared satellites making infrared surveys of the sky. And what we actually see, of course, is millions of natural objects which look like artificial biospheres as far as we can tell, but there's no reason to think they're artificial. What they actually are is just dust clouds enclosing stars. When stars are formed out of dust clouds, as most of them are, the dust remains for a long time after the star starts to shine. So the dust heats up and radiates away the infrared on the outside, and that's what we see. So these are almost certainly natural objects. And I don't know of any good way of telling the difference between a natural and an artificial source.
At one point you mentioned the idea of a universal constant, that the universe would constantly be accelerating. How does it work that if the universe is constantly accelerating, there should be a speed, the speed of light, at which it stops? So how does the theory reconcile that?
So the theory doesn't say that anything stops. What happens is that if you're, the speed of light is the speed limit for any particular object. So what happens is, but it's not a limit for the universe as a whole. So what happens is that if you have a galaxy which is moving away from us today, say at 50,000 kilometers per second or something like that, that it will gradually move faster and faster as it moves away. And exactly when it gets to light speed, it will disappear over the horizon so that you'll never be able to contact it anymore after that. So it is actually, if you like, you can say it does exceed the limit after it gets over the horizon. It no longer belongs to our universe. So that's the way the thing works. Yes.
What about when our galaxy reaches that speed? Will we disappear too, or will we come in contact with all those other galaxies that have already gone?
Well, because velocity is speed is only measurable relative to something. So our speed, as we measure it, won't get any greater. The galaxy, as we measure it, in fact, it will, as time goes on, it will evolve. So the outer parts of the galaxy will move out gradually, and the inner parts will collapse gradually. But nothing will ever get close to the speed of light. But of course, any other galaxy looking at us will see us disappear over their horizon, but their horizon is not the same as our horizon.
Hi, I was at the recent Pugwash conference where we discussed nuclear weaponization, and I would like to know your take on the issue and how you recommend a student like me raise awareness about it.
Wonderful. I'm so happy that somebody's doing that. I mean, nuclear weapons have become sort of unfashionable as a thing to worry about, and I'm happy that somebody is actually worrying about it, especially somebody young. And no, this is still a profoundly important problem, of course, and we ought to be getting rid of our nuclear weapons. it is a great shame that the public has kind of lost interest in that. And I used to go to Pugwash meetings when I was a little bit older than you are, and it was in those days, of course, it was profoundly important that we did talk to the Russians and the Chinese. We came to some agreements among ourselves, which have been helpful, I think, in keeping the thing under control. But it still remains true that there's a huge danger of a major nuclear war, which it's still the most dangerous of all the dangers we have to worry about. And we still have far too many nuclear weapons in the world. We ought to be negotiating to get rid of them. And it's just a shame that we've given up on that.
Thank you.
So I hope you'll continue to get involved with Pugwash and other things of that kind. I mean, Pugwash is because it's changed a lot in the last 50 years. In many ways, it's doing a lot more than it used to do, but it's getting a lot less attention, and that's unfortunate.
I just wanted to go back to something you mentioned earlier. You mentioned a theory that biology determined psychology and that you didn't agree with that. Would you in turn think that our psychology determines our biology, that our science is influenced by our psychology? What do you think the relationship is?
Well, I would say that they're to a great extent independent. It's, of course, there's always some connection between adjoining fields. But I mean, my own feeling is that the biological way of looking at things, of course, is quite different from the psychological way of looking at things. That in biology, you're looking at the structures and the functions of individual components in the brain. I mean, if I'm thinking of neurology, which is most closely connected with psychology. Neurology is about neurons, and it's about how the neurons function and how they're connected together, how the system works, but as a system with components. Whereas psychology is sort of how it looks from the point of view of the individual, describing the behavior of humans as humans see it, so the concepts are different. There are connections, but I think it would be a mistake to try to reduce the one to the other. I heard a very interesting talk just recently by a fellow called Jeffrey Miller, who is a psychologist, and his view is that the human brain is actually a fitness indicator, and well, this is, I think, it's a good example of a bright idea, which even could be correct, that the human brain didn't evolve in order to be useful. It didn't evolve so that we could survive by inventing clever tricks. It evolved so that we could show off, like the tail of a peacock. And the tail of a peacock, you see, is what's called a fitness indicator. It's disadvantageous to the peacock to carry this monstrous tail, but it's important as a fitness indicator for showing the female that this guy really has what it takes. And so the human brain is the same thing, that it's a device for attracting the girls, or in the case of a girl, it's a device for attracting the boys. And it enables you to put on a good show while you're sitting around the fire in the cave, and telling great stories and singing music. And so it explains why our brains are so well constituted for singing and music and dancing and all the ornamental faculties, and so badly adapted to doing differential equations.
What are your views on the theory of dark matter, dark energy creating dark matter in the depths of space, spontaneously creating matter without there being matter already created?
Well, that's a sort of a complicated question. I'll tell you what little I know. There are two quite different things. There's the dark energy, which is this mysterious accelerating force that we just don't know anything about. which might be quintessence or might be something else. So that's simply an unknown quantity, unknown in its nature. The dark matter, is something we know a little bit more about. We see its gravitational effects, and we can localize it to some extent. We know it exists around clusters of galaxies and around single galaxies. We can see its gravitational effects by making gravitational lenses and things of that kind. And so that's real. The question what connection there is between them, we have absolutely not the foggiest notion about. So there's no reason to believe that dark energy is creating dark matter. That certainly isn't part of the standard dogma. I don't think it's probably true. I mean, the dark matter probably has existed right from the beginning. The dark energy becomes, you can't say, it probably has existed, but of course it fills the whole of space more or less uniformly. So you can't say that it's produced anywhere in particular. So the two things are quite separate. And all you can say is we know a little bit more about the dark mass than we do about the dark energy. Both of them, probably all of what will happen in the end, we'll find out things are quite different from what we imagine them today.
I can't resist repeating one of the questions a student asked about whether we'll ever be able to travel backwards in time. That was an identical question asked to Steve Hawking when he was here. And his answer was typical. He said, no, I don't think we'll ever travel backwards in time because if it were possible, we would already have been visited by people from the future, which is a more... Yes, maybe we are. There's some people here I'm suspicious of. I do want to ask a final, unless you have any comment on it.
No, I agree with that. That's a good answer. Yes, as usual, Stephen is right.
That's correct and funny. I do want to repeat a question that Stephanie asked yesterday. You're surrounded by exceptional students here, and we're broadcasting this to 13 other schools, so there's a large audience, and it's conventional for us older people to give advice to young people. So we thought maybe in your last of the afternoon here, you might project what would be interesting for these people to be concerned with over the next 10, 20 years.
Yeah, well, I don't know whether I should repeat what I said to the other class or try to think of something different. Are the same people listening? Or, no. All different. Good, okay. Well, I think I'll say what I said before. Well, there were two things. First of all, go out in the world and learn foreign languages and become citizens of the world. This, as I come from overseas, of course, but I've seen this country somehow get more and more inward-looking during the last 50 years, and that worries me profoundly, that this country is so concerned with itself, so little concerned with the world outside, and there's so little genuine knowledge of what's going on in the rest of the world. And that's, of course, most of the rest of the world is much more in touch, because they have to be. The rest of the world is generally, the countries are smaller and closer together. They have to learn foreign languages. They have to be much more aware of the rest of the world and how the rest of the world feels. So I hope each of you will take a chance as much as you can before you've become old and incapable to go out there and learn foreign languages and get familiar with foreign cultures and bring back your understanding to this country. And of course, science is an international enterprise, and it's extremely, one of the best things about being a scientist is you become a member of this international club, and so you will have a chance to go travel. You'll have friends and colleagues everywhere, interesting places like China and Japan and Africa, all over the world. There are places, not just Europe, where you'll have friends and colleagues. So make the most of that and become familiar and look at things from their point of view as well as ours. The second thing I was saying this morning, which is also important, is that writing is an essential skill in the modern world. It's not true that books are obsolete. It's a strange thing. always being told that because everybody is online, that you won't have the books won't be important anymore. It seems that books are just as important as they ever were, and written communications in many ways is more important. I have these 6 kids of mine who are all in different professions, but they all are doing well in a sense because they are able to write. That whether you're a doctor or a lawyer or a business person or a professor or a veterinarian, whatever you're doing, being able to write a good, clear, coherent account of what you're thinking is extremely important. And in fact, it's what gives you power, and very often power comes directly from being able to write. So, and in addition to that, of course, writing books enables you to make friends, and it opens a lot of doors, as it happened to me. So I encourage you to cultivate your skills in writing, practice, and write as much as you can, even if it's only letters to your mother. It's good practice, and it's in the long run it's going to be essential to your doing well in science and everything else.
I'd like to thank you, Freeman, for your